guys, it's Kayla
and Jim,
and welcome back to another Meteorology Monday. What are we talking about today?
Today we're going to talk about the 1974 super outbreak here in the United States, and that was requested by some of our subscribers as well as other folks that haven't subscribed yet, and we're wondering why you haven't subscribed yet. So again, today we're going to talk about the 1974 super outbreak, which involved over 140 tornadoes across 13 U.S. states and Ontario, Canada, within roughly 18 hours, killing 319 people and injuring 5,484 more. Damage totaled roughly 843 million US dollars, equivalent to $4.58 billion in 2019, with more than $600 million, equivalent to $3.3 billion in 2019, occurring in the United States. It was an incredible event that set the bar for most number of tornadoes in an outbreak up until the 1981 United Kingdom tornado outbreak, and in the United States until the 2011 super outbreak. There are also a number of other incredible events that happened, some record-breaking.
So if you're a longtime watcher of our channel, you'll know that we've already done a case study on the 2011 outbreak here in the United States. But let's go back to 1974 and see what the bar was before 2011.
So let's give a brief overview of the event, as this was a very, very significant event affecting many states. So let's talk about the time frame of this. Again, it was April 3rd through 4th, 1974. But as you'll see, there's actually some setup a couple days in advance before the main event, which isn't really discussed a whole lot in the April 3rd to 4th time frame, but we'll get into that soon. There were many, many people that were killed, many injured. It lasted a long time, over the course of, again, 18 hours. So this is going to be quite an interesting case study.
And if you guys are familiar with this event, you're probably familiar with some of the tornadoes that came out of the super outbreak, such as the Xenia, Ohio F5, the DePaul, Daisy Hill, Indiana F5, the Hanover, Madison, Indiana F4, the Brandenburg, Kentucky F5, the Cincinnati and Sailor Park, Ohio F5, the Louisville, Kentucky F4, the Tanner, Alabama F5, the Jasper, Coleman, Alabama F4, another F5 tornado in Tanner, Alabama, and the Gwynn, Alabama F5. So that's just a short list of the amount of devastating tornadoes on this day, and some of the ones with the bigger names that people might recognize.
That's right, and there was a lot of major tornadoes with this outbreak.
Again, if you've watched the other case studies that we've done, normally there's only a few major tornadoes in these types of outbreaks, but this super outbreak, incredible amount of damaging tornadoes.
So let's take a look at the setup for this extraordinary event. On April 1st and 2nd, 1974, a powerful low-pressure system developed and moved into the Mississippi and Ohio Valley areas of the United States. This caused a surge of unusually moist air to ride northward from the Gulf of Mexico. The combination of a strong cold front, warm moist air ahead of the system, and upper air dynamics caused an outbreak of tornadoes across portions of the Ohio Valley and the South, including 3 killer tornadoes in Kentucky, Alabama, and Tennessee. Several F2 and F3 tornadoes occurred, including one F3 that destroyed a large portion of the town of Campbellsburg, Kentucky, northeast of Louisville. Behind this storm system, an upper-level trough was rapidly moving over the Great Basin area of the western United States and deepening. An associated surface low-pressure center was located over southeastern Utah, with a cold front extending southwestward through northwestern Arizona and southern California. Over the southern Rocky Mountains, a very strong mid-tropospheric jet stream was present and would contribute to intensifying the low-pressure center, deepening it 10 millibars as it moved over eastern Colorado. The low continued to deepen as it moved eastward into central Kansas during the early morning hours of April 3rd. A shallow, dry polar air mass to the north and west of the low allowed for a wide band of snow, which was heavy at times. As the cold front continued moving eastward across Texas at an average speed of 30 knots, 35 miles per hour, or 56 kilometers per hour, a rapid influx of low-level moist air from the Gulf of Mexico was surging northward. Combined with the strong upper-level jet stream, this would set the stage for the super outbreak that was to ensue over the next 24 hours. Several hours before the outbreak, there was enough dynamics ahead of the system to spawn an additional tornado in Indiana during the early morning hours of April 3rd. At 7 a.m. Central Daylight Time on April 3rd, the strong upper-level trough had extended over most of the continental United States, with several short waves rotating around the base of the trough. The low-pressure center over Kansas deepened to 980 millibars, and the winds at the 850 millibar level increased to 50 knots, or 58 miles per hour, 93 kilometers per hour, over portions of Louisiana, Mississippi, and Alabama. A warm front had extended eastward across northern Arkansas, Tennessee, and the Carolinas. A cold front had extended southward from the Oklahoma-Arkansas border through East Texas. Significant moisture advection was occurring across the deep south, Arkansas, and Tennessee. As the air destabilized, Cape levels rose to 1,000 joules per kilogram. However, warmer temperatures aloft kept thunderstorms from initiating at the surface. Overnight, a large mesoscale convective system, MCS, developed over Arkansas and strengthened as it moved into an area of strong environmental lapse rates. What is a strong environmental lapse rate? Let's talk about that in just some general terms. A strong environmental lapse rate has to do in terms of the vertical profile of the atmosphere over a single point. And really, if you want strong thunderstorms to erupt, what you want is warm, moist air closer to the surface, and you want cooler, dry air aloft or above that. And so that causes the atmosphere to be out of balance, and it wants to put the cold, more dense air at the surface and the warmer air above. So what you need is a trigger to make that happen, to make that convective overturning start to happen. And can you guess what that triggering mechanism would be?
The cold front, the short waves,
the
trough, anything like that could trigger this, but the combination of all of these is what leads to such big events like this.
That's right. The low-pressure center filled slightly and moved rapidly northeastward toward Lake Michigan. The surface cold front continued moving eastward rapidly across the mid-Mississippi and Ohio valleys. Cold, dry air swept in and collided with the warm, moist Gulf air established over the Ohio and Tennessee valleys. The collision of these air masses would eventually develop at least 3 extremely intense tornado-producing squall lines. As the morning of April 3rd ensued, severe weather watches were being issued by the National Severe Storms Forecast Center across the Ohio and Tennessee valleys, while portions of the upper Midwest were reporting snow. Heavy rain was falling across central Michigan and much of Ontario. At 8:27 a.m. Central Daylight Time, the National Severe Storms Forecast Center issued the first severe weather watch of the outbreak, number 92.
So in that section we just talked about a squall line. Well, what is a squall line? Basically, it is just a line of thunderstorms that we put a fancy name on it. Also, sometimes we call this a band of storms. So as we're about to see, the NWS does refer to this as a band. So when it's talking about that, think squall line and a line of kind of unbroken thunderstorms that just plows through an area.
That's right.
Let's get into the details of the first band of storms.
At 8:42 a.m. Central Daylight Time, a large MCS was located over Indiana, eastern Illinois, and western Kentucky. As the storm system moved further east that morning, it encountered a few factors that would cause it to split into a northern system and a southern system. The factors for the split were areas of subsidence over eastern Kentucky and western West Virginia, and local downsloping winds and a temperature inversion over the Appalachian Mountains. These two systems would eventually become the first intense tornado-producing squall line, Band 1. Numerous supercells began to develop across the southern area, with one supercell producing an F3 tornado around 11:30 a.m. Central Daylight Time near Cleveland, Tennessee. By 12:53 p.m. Central Daylight Time, the MCS separated into 2 sections, with the northern section accelerating east-northeastward at 60 knots, or 69 miles per hour, 111 kilometers per hour, toward eastern Ohio and western Pennsylvania, while the southern section slowed down its forward progress as it approached southeastern Tennessee. Later in the day, the second band would eventually catch up to the southern section of the first band located over Alabama, Georgia, and eastern Tennessee. While Michigan was not as hard hit as surrounding areas, they did see their share of nasty weather. One deadly tornado was reported near Coldwater and Hillsdale, killing people in mobile homes. Heavy downpours from thunderstorms caused flash floods, and heavy snowfall was reported in the Upper Peninsula due to their proximity north of the warm front. So with that first band, we got a lot going on.
Already, yeah.
On the north side, north of the warm front, we've got heavy snow occurring. You've got a transition over to severe weather. This is already just one part of the storm. We still have two other bands to talk about here, and this is earlier in the day. So we're not even 1 o'clock in the afternoon,
right,
and it's already popping. So this is an extraordinary event. Lots of dynamics going on here.
I can't imagine it being snowing 1 second and then severe weathering the next. That just, it seems crazy to me that you can have a snowstorm and tornadoes within a very short time period.
And there are cases where it actually snowed and then the warm front went through, they got into the warm sector, severe storms came through, hail, tornadoes, and then it would go through and it turned cold again. Or severe storms rolled through with tornadoes, and then it would snow on the backside of the storm. It just
Weather's
incredible,
weird.
incredible events.
Now let's talk about band number 2.
Around 10 a.m. Central Daylight Time, April 3rd, a new band of scattered thunderstorms developed over eastern Arkansas and Missouri. Behind the MCS that moved through this region earlier in the day, the wind started backing at the low levels, while daytime heating caused rapid destabilization of the lower atmosphere. It is also suggested that cool mid-level advection had occurred over the warm sector ahead of the band, which strengthened the lapse rate, aiding in rapid upward motion. By 1 p.m. Central Daylight Time, CAPE values were in excess of 2,500 joules per kilogram over the lower Ohio and Mississippi valleys. With favorable wind profiles due to the backing of low-level winds, helicity values increased significantly to over 230 meters squared per second squared. All of these combined are very favorable for the formation of tornadic supercells. Between 10 a.m. Central Daylight Time and 2 p.m. Central Daylight Time, several intense supercells formed along the second band across Illinois, Indiana, and northern Kentucky. Several tornadoes formed, including the first F5 tornado of the day, which occurred at 2:20 p.m. Central Daylight Time near DePaul, Indiana. In fact, several storms that formed between 2:20 p.m. Central Daylight Time and 3:20 p.m. Central Daylight Time became significant, long-lived supercells that produced many strong or violent tornadoes. 3 F5 tornadoes formed and devastated the towns of DePaul, Indiana, Xenia, Ohio, and Brandenburg, Kentucky. By 4 p.m. Central Daylight Time, the second band had extended from Ohio southwestward to Mississippi, and within the next few hours it would catch up to the southern section of the first band over Alabama, Georgia, and eastern Tennessee. The atmosphere in this region was experiencing increasingly west-southwesterly wind shear at all levels in combination with outflow boundaries from previous supercells. This would allow new supercells to form and produce strong, long-lived, long-tracked tornadoes. As the evening progressed, these storms would go on to produce some of the most powerful tornadoes of the outbreak. Some of the most notable storms would be a large and long-tracked F4 that struck the western and central portions of Alabama, tracking just over 110 miles, 178 kilometers. 2 F5 tornadoes that devastated Tanner, Alabama, causing numerous fatalities and injuries. An F5 tornado that almost wiped out Wynne, Alabama, and many other violent, deadly tornadoes causing many more fatalities and injuries in Tennessee. Okay, so we had our first band go through earlier in the day. The southern portion of that is getting caught up down over the deep south, and now we have the second band that is marching through in the heat of the day, causing a whole lot more storms, a lot more stronger storms, more powerful, long-lived, long-tracked tornadoes, and it's also catching up to that the southern part of the first band. So a lot is going on, and watches and warnings are just popping up all over the place at this point. It's incredible based on the report that they put together afterwards on how much these National Weather Service agencies were trying to keep up, along with emergency management and everything. It was just incredible. Around 11 a.m. Central Daylight Time, April 3rd, a third convective band formed and extended from west central Illinois to St. Louis, Missouri. Based upon satellite imagery and atmospheric model data, differential positive vorticity advection was moving through this area, combined with the left exit region of the upper level jet stream, which reached wind speeds of up to 130 knots, 150 miles per hour, 241 kilometers per hour. These dynamics initiated the growth of the third band. As the storms grew in intensity, some produced baseball-sized hail in Illinois around 12:20 p.m. Central Daylight Time, and also in St. Louis, Missouri a little bit later. Although the St. Louis storm did not produce a tornado, it was recorded as the costliest storm to hit the city up to that time. By 1 p.m. Central Daylight Time, the line of storms stretched from central Illinois southwestward to eastern Missouri. As the storms continued to move eastward, supercells producing F3 tornadoes hit the cities of Decatur and Normal in Illinois by 2:50 p.m. Central Daylight Time. As the storms encountered more warm, moist air over eastern Illinois and Indiana, they produced long-lived tornadoes, one of which began near Otterbein, Indiana, and ended near Valentine, Indiana, a distance of 121 miles, or 194 kilometers. By 7 p.m. Central Daylight Time, April 3rd, deep low pressure was located over southeastern Iowa with a triple point in central Illinois. A warm front extended from the low center northeastward into Wisconsin and the central lower peninsula of Michigan. A second warm front extended from the triple point eastward through northern Indiana, central and southern Ohio, and into the mid-Atlantic states. A cold front extended southward from the triple point through the middle and lower Mississippi Valley. As the evening continued on, the activity across the southern United States moved across the Appalachians during the overnight hours and produced the remaining tornadoes across the southeast U.S. during the morning of April 4th. By 7 a.m. Central Daylight Time on Thursday, April 4th, it appeared the original cold front had dissipated and reformed 100 miles to the west over the central Ohio and Tennessee valleys. This was due to a second 500 millibar trough moving across the Great Plains. As the trough moved eastward, it met up with the reformed cold front, which then moved eastward, crossing the Appalachians and off the east coast on April 5th. This cold front moved at a slower pace, 10 to 15 knots, compared to the original cold front, 30 knots. Since most of the dynamics were less in comparison to the previous 48 hours, a tornado outbreak did not occur east of the Appalachians with the second cold front. Later studies by Dr. Ted Fujita in 1974 and 1975, as well as a survey by Risk Management Solutions citing Dr. Fujita's studies, found that 3/4 of all tornadoes in the 1974 super outbreak were produced by 30 families of tornadoes. These families were defined as multiple tornadoes produced in succession by a single supercell, with the majority of these single supercells being long-lived and long-tracked.
So that third band was a lot to digest. Not only were there lots of big words in there, but there was also a lot of stuff going on during the event. As it said, you had a cold front that kind of moved over the Appalachian Mountains and towards the coast, and then another low pressure system and trough formed back over the middle of the United States, and the cold front jumps back and forth and it moves in again, and then we're talking about families of tornadoes. So let's kind of just break it down a little bit, and let's talk about the family of tornadoes. Like it said, that's one supercell that just keeps producing tornadoes over and over and over. We touched on this a lot when we talked about the tri-state tornado in our last case study, and how that one wasn't a family of tornadoes. This one actually was.
Yeah, good example, good contrast between that case study and this case study. One thing when it's just one continuous, that's incredible in its own, but this event having so many, 30 family of tornadoes producing 148 tornadoes.
And they were long track tornadoes too. One
and
of them
strong.
was like 121 miles long, and they're extremely strong tornadoes, extremely devastating. But the dynamics behind this storm, the fact that it was able to just keep these storms going for so long, really like a testament to what the atmosphere was that day and how much warm air they had coming through, how much CAPE, which is convective available potential energy, that was high, helicity was high. Again, we're getting into a bunch of terms here that might be a little bit more technical. If you have any questions about the specific terms, leave them in the comments below and we'll get to them. But if you're somebody who's studied meteorology, you know those numbers are incredible for an event like this.
So it's really interesting nowadays when we talk about technology, things have improved so much, but with a situation like this, let's take a look at what the National Weather Service as well as folks there that had to deal with using 1974 technology. Here's one thing I found very interesting in this study, and that was specifically about how the satellite data was used. The NASA Geostationary Applications Technology Satellite number 3, ATS-3, was used for satellite imagery and was only available during daylight hours. Now that's very interesting.
Yeah.
So nowadays we're used to satellites. Daytime imagery is with the visible, but infrared goes 24/7. So, we're used to seeing satellite images 24/7. But back then they didn't have that. They only had it during the daylight hours. One day prior to the outbreak, so April 2nd, a request was made to have the ATS-3 satellite be committed to a tornado operational mode for the following day, April 3rd. On the day of the outbreak, pictures were taken every 13 minutes instead of the normal 30 minutes, from 1:49 p.m. Central Daylight Time to 6:24 p.m. Central Daylight Time, at which time insufficient illumination over the outbreak area forced discontinuation of the operation. So the sun was setting and the satellite did not have enough illumination from the sun for them to be able to continue that operation. That's one thing, part of this. The second thing is that they went from taking pictures or images every 30 minutes to every 13 minutes. Now back then, that time resolution was amazing. I mean,
back in the day.
Nowadays we get them every minute, but back in the day, boy, 13 minutes, that was incredible. This was the technology that they had to use to make sure that people were safe and that property was protected. The pressure put on the National Weather Service folks, the emergency management personnel, and everyone else that was involved to try to keep the public safe.
Another thing is that the NWS radars back then did not have Doppler technology, so you could not tell that the winds were going in different directions. Nowadays, we use that a lot to show rotation in storms and to be able to tell which storms have the potential to be tornadic or already have tornadoes on the ground.
Not only that, some of the radars needed continuous maintenance. These things are going and they're scanning the skies continuously. They would break down, and I saw a report, or within this report, they had mentioned that there was one mechanic that was working on this radar continuously for hours and hours to make sure that it was up and running. But there were some radars that actually did wind up failing, and so you had a gap in certain areas for a certain period of time during the outbreak. Flying blind in this major outbreak is, I mean, it's scary. You're trying to do your job and you don't have the tools to do it with. And this was the main event that really caused the National Weather Service's modernization program to get a jump start and to move forward. Because if it happens once, it can happen again. And
it did happen again.
Yeah, and they don't want to be caught like this again. They want to make sure they have the right tools. And so this sparked that development and then pushing it out operationally to what we have nowadays.
And 40 years later, in 2011, this new technology actually did make a difference. So there you have it, the 1974 super outbreak. Very, very interesting case study. Again, thank you to everybody who suggested us doing this case study. I know I enjoyed reading through it and learning about this. I know you did as well. If you like what you saw, be sure to give this video a thumbs up and subscribe down below so you never miss another case study like this. Follow us over on Facebook and Instagram, popping up here, as well as our website, and all the articles that we're reading will be linked down below. Until next time, I'm Kayla.
And I'm Jim.
Thanks for watching.
And we'll see you at the next Meteorology Monday.
What is a squall line?
What is a squall line?
I know what a squall line is, but how do I describe a squall line?